7.2 practice problems. The particle diagram above illustrates the changes that takes place when X and Y are placed in a rigid container at constant temperature. Which of the following is a characteristic of a system at equilibrium that is best represented by the particle diagram? So, as I look at the particle diagram, I can see that at time 0, I have all reactants, no products. At time 100, I am starting to see products. I have 2 products here. At time 200, I have 3 products here. At time 300, I have still 3 products. And at time 400, I have 3 products. So what I am looking for in my answer is something that states that my forward and backwards reactions are the same when I am at equilibrium, and wherever that happens along here is when equilibrium is reached. Since starting at time 200, I have 3 products, and I do not increase or decrease my number of products starting there. I'm going to look probably for an answer that says something about time 200. So option choice A says the particle diagram shows that initially the reaction proceeds in the to the right to form products, which is the characteristic of a system at equilibrium. Nope, that's just the characteristic of a reaction proceeding forward. Option B says the particle diagram shows that after 200 seconds, the rate of the reverse reaction is slower than the rate of the forward reaction, which is a characteristic of a system at equilibrium. Nope. The rate of the forward and the reverse reaction need to be the exact same to be at equilibrium. Option C says the particle diagram shows that after 200 seconds, there are no observable changes in the amounts of reactants and products, which is a characteristic of a system at equilibrium. This sounds pretty good. Again, we are looking for no change in concentration since the rate forward and the rate back is the same, so that does match. Let's see if option D is any better. Option D says the particle diagram shows that between 0 and 200 seconds, the rates of the forward and reverse reactions are the same, which is a characteristic of a system at equilibrium. So we know that that is definitely not true. At time 0 here, we had no products, and at time 200, we had 3 products there. So the rate is definitely different between time 0 and time 200, leaving me with just answer choice C, which again stated that I don't see any changes in concentrations, meaning that my forward and reverse reactions are at equilibrium. An equimolar mixture of X and Y is placed in a rigid container at constant temperature. The particle diagram above represents the changes that occur over time. Based on the particle diagram, which of the following best predicts whether or not the system has reached equilibrium by 300 seconds? So as I look here at time 0, I have 0 products. At time 100, I have 1 product. At time 200, I have reached 3 products, and at time 300, I have reached 4 products here. So since I don't have any of these measurements where I have the same number of products and reactants in comparison, I have actually no idea if at time 300 I've reached equilibrium. I would need another measurement of time past time 300, where those quantities are the same in order to confidently be able to say that it's reached equilibrium. So I'm going to look for something that says something along those lines. Option choice A says it's not possible to determine that the system has reached equilibrium by 300 seconds because the stoichiometry of the reaction is not known. My stoichiometry is not what determines if I am at equilibrium. Again, it is if my forward reaction and reverse reaction are at the same rate, and therefore I would not see a change in concentration forward and reverse. Option B says it is not possible to determine that the system has reached equilibrium by 300 seconds because the amounts X, Y, and XY have continued to change. Now this does match what I previously predicted, so that sounds pretty good at this point, but we'll see if there's anything better. Option C says the system has reached equilibrium by 300 seconds because the rate of formation of XY is constant. That is very much not true. Again, we have a different number of products in each of our time samples, and so that is definitely not true. Option D says the system has reached equilibrium by 300 seconds because the rates of consumption of XY are equal. No. So, again, it's not about how much of the reactants are being consumed. Instead, it is the rate of forward reaction versus the rate of the backwards reaction that determines if I'm at equilibrium. And I cannot determine that since I do not have any of my time samples where my amount of products remained consistent. So option choice B is going to be my best choice. The reversible reaction is represented by the equation above. The amount of reactants and products at time 1 are shown in the particle diagram on the left. The particle diagram on the right shows the amounts of reactants and products at time 2. Based off of the diagrams, what can be inferred about the relative rates of forward and reverse reactions between time 1 and time 2? So we know that our product here is going to be this XY here. So I have 1, 2, 3, 4. And in time 2, I have 6 total. So I know that I have definitely not reached equilibrium, okay, because then it would be the same. And instead, I know that I am continuing to proceed forward to the right. So my reaction is still generally in the forwards direction, and I am still making more product. So I'm going to look for something that says something along those lines. Option choice A says nothing can be inferred because the total number of X and Y atoms is the same in each diagram. No, the products versus reactants and stuff does change, and even if they didn't change, we could infer something about that. So no. Option choice B says nothing can be inferred because the temperature of the system may have changed. That would change potentially if I was more favoring toward my forward or reverse reaction. However, I can still infer something about this overall situation based off of the number of each type of molecule that is present. Option C says the rate of the reverse reaction is greater than the rate of the forward reaction. We know that that is, in fact, the opposite. Since I did make more products, my forward reaction is going to be at a higher rate than my reverse reaction. And then option choice D says the rate of the forward reaction is greater than the rate of the reverse reaction. That is going to be my answer choice since, again, I did create more products and therefore the rate of the forward reaction is greater than the rate of the reverse reaction.